So this is the first section in the methods in calculus chapter, and this is dealing with improper integrals. Now, improper integrals come in two types. So improper integrals. Right, so what are the two types? Well, one type is where one or both of the limits are infinite. Okay, so we've got this symbol as one of the limits. So for example, here's some examples here. So let's say I had to integrate something between 0 and infinity, some sort of function there, or let's say it was from 4 to negative infinity, or it might be that both of the limits, it goes from infinity, positive infinity, to negative infinity. Okay, so that's one type of improper integral. Another type of improper integral is where the integral is not defined at some point. Okay, so the integral is not defined for some let's get my English right, it's not defined for some value or values. Yes, it could be a single value that it's not defined for, or it could be more than one value that it's not defined for. So here's an example. Let's say I wanted to integrate something from 0 to 8, no problem with the integrals, but let's say it was 1 over x. I'm trying to integrate that. Well, there's a problem, isn't it? Because I know that 1 over 0 is not defined. Okay, so there's going to be an issue there. Another one might be, let's say that I was integrating from 9 to 20, and the thing that I was trying to integrate, let's say it was 2x over x minus 9. Okay, well, this is not going to be defined when x equals 9, because you'll end up dividing by 0. So there's a problem here, because when x equals 9, which happens to be that lower limit, we end up doing 2 times 9, which is not a problem, and then 9 minus 9 at the bottom, divide by 0. So there's going to be the issue. So these are two types of improper integrals. Okay, and so how do we deal with these? Well, what we do, if it's the first type where we're dealing with limits which are infinite, what we do is we replace the infinity sign with another parameter letter, and we're going to use t, and then what we do is to see what happens as t, or as what's the limit as t approaches infinity. If it's to do with a function that's not defined at some point, then what we do is we replace the problem value with t. So replace problem value with t. So that's normally the limit that we're going to change. Well, it's always going to be the limit. So for example here, I would replace the 0 with t, because that's the problem limit there, because that's not defined. Here I would replace this limit here with t, and what we do is we see what happens as t approaches. Now this time it's not approaching infinity, it's going to be as t approaches the problem value. So for this example here, we would replace this with t, and then we'd look to see what happens to this as t approaches 0. For here, we would see what happens as t approaches 9. Now, sometimes when we evaluate the limit as t approaches whatever value it is, when it's not defined, or when it's infinite limit, one of two things will happen. We'll either get a value that converges as t approaches the limit. Okay, so it might converge to a value as t approaches the limit, or it might not converge, it may diverge as t approaches the limit of infinity, or whatever problem value it is. Now, if it converges, then what that means is that there is the improper integral has a value that it converges to, so we can evaluate the value of the integral if it converges. If it diverges, we cannot evaluate the value of the integral. Okay, let's have a look at these examples. So the first one says, evaluate each improper integral or show that it is not convergent. So if it's not convergent, that basically means that it's divergent, and we can't evaluate the improper integral. So the first one, you can see that it's an improper integral because that upper limit is infinite, and we want to see what happens when we replace that upper limit with t. We're going to see what happens as t approaches infinity. It may be that this value converges, it may be that it doesn't converge, it diverges. So step number one is to replace that upper limit, the problem limit, with t, and we must write down that we've replaced it with t because we want to see what happens. What's the limit as t approaches infinity? So as it approaches this problem limit here, because as it stands, we can't evaluate this. We can't just sort of integrate this and just substitute infinity as a limit. It doesn't make sense. We want to see what happens. What's the limit? Where does it go to? Does it converge or diverge? So first thing to do is to then integrate what we have, and at each step we should write down that, you know, where it's the limit as t approaches infinity or whatever value it needs to be. So 1 over x squared, well, that's the same as x to the power negative 2. That's probably going to be a bit easier to integrate. So x to the power of negative 2 integrated, well, we'll add 1 to the power, divide by the new power. So this becomes the limit as t approaches infinity of, so what we're going to evaluate now is negative x to the power negative 1, and our limits are 1 and t. So next step, maybe let's write this in a form that's easier to understand. So I'll write it as negative 1 over x. Now the reason I'm writing the limit like that, because with the help of a graph it's easier to see whether this negative 1 over x converges or diverges, and graphs are often useful in this type of question. If you can sort of draw or visualize the graph, it will help you work out whether it's going to converge or diverge. So we now substitute in the limits. So that's going to be the limit as t approaches infinity of, and that will be 1 over negative t minus 1 over negative 1. So all I've done is substitute in those limits. So this is just like normal integration, so you can see that these are the limits here that have just been substituted in. And we want to see what happens. Basically, the important bit is this bit here. What happens as that approaches infinity? Well, if we know something about this graph, or we know something about what's going to happen as this gets bigger, we know that if this value here gets bigger and bigger and bigger, the whole fraction itself is going to get smaller. So as this approaches infinity, the actual whole fraction approaches 0. That's going to be its limit, is 0. So I'm just going to write down this, an explanation of what I've just talked about there. As t approaches infinity, 1 over, or negative 1 over t approaches 0, or you could say negative 0. So what happens is we actually end up with just, let's write it out in full. So we'll end up with basically 0. So this is going to be the limit now as t approaches infinity. So the first bit becomes 0 minus negative 1. So the final answer for that is 1. So this one converges, and its value is 1. So there's our final answer for that one. So we can now go on to part B. So part B is just a different function here. It's just 1 over x. So we want to evaluate 1 to infinity. Now you'll notice that a problem value for x, just like in the first one, would have been x equal to, or a limit equal to 0. But in this question, the lower limit has been chosen as 1 to avoid the problem of this not being defined. So at the moment, we're just looking at the integral, but later on, we will be looking at examples where one of the limits may be 0, or a value that's going to make this not defined. But in this question, it's not an issue because that limit is 1. Right, so we should know from our normal maths that when we integrate 1 over x, it becomes log x. So straight away, we're going to replace the infinite limit with t. And as soon as you do that, you must write down it's the limit as t approaches infinity. And it's 1 over x dx. So we'll integrate that. So it's still the limit as t approaches infinity. And it's going to be putting the limits into log x, because that's what 1 over x integrated becomes. So 1 and t. So now we put those in. So we'll end up with the limit as t approaches infinity of this. So log t, just looks like int, doesn't it? Minus log 1. Now log 1 is 0. So we want to see what happens here as t approaches infinity. Now this is where it helps maybe knowing a bit about the graph of log t. So let me just draw it down here. You may already know what the answer is going to be. So this is log t like this, okay, crossing at 1, and it goes up forever. Yeah, so basically as t goes off to infinity, so this would be t on this axis here, log t goes off to infinity as well. So it doesn't converge. So let's just write a sentence down to explain what's happening there. So as t approaches infinity, log t approaches infinity. So we can say, therefore, the integral or improper integral is divergent, or it doesn't converge. So it cannot be evaluated. Okay, so therefore the integral is divergent, so it cannot be evaluated, unlike the first one. So I'm guessing this bit here will be our final answer for that. Right, so let's start with the first one here, a, and we've got limits of 0 and 1, and it's 1 over x squared. So for this one in a, we can see that this function is not defined for x equals 0. So the bottom limit is the problem. So in part A, the lower limit, and that's the limit of x equals 2, is the problem, as 1 over 0 squared is not defined. So since it's not defined, we need to replace that lower limit with t. And what we want to do is to see what happens as that lower limit of t approaches 0. So next step is now to write out, we're now introducing t, and we want to see what happens as t approaches 0, because that's when the function, the integral, is not defined. So 1, t is our lower limit there, then 1 over, and actually let me write this as x to the power negative 2, because that's just going to be easier to integrate when it's written like that. So the limit as t approaches 0. Now x to the power of negative 2 integrated is going to be negative x minus 1. Remember, add 1 to the power, then you divide by the new power, so I'm effectively divided by negative 1. And limits of 1 and t. Now if I write this as negative 1 over x, it's easier to see what goes on as t approaches 0. So this becomes negative 1 over x, like this, 1t. So this becomes the limit as t approaches 0, and it will be negative 1 over 1, that's the first bit, minus negative 1 over t. Let's write this in the next row down. There we go, it's written down here a little bit clearer, a bit too squashed up where it was before. So what are we looking at? We want to see what happens as this approaches 0. Now as this approaches 0, this fraction is going to get bigger. It's not going to converge, it's going to diverge. So the whole thing is going to diverge. So we need to write that down as, to explain what we're doing next. So we can say, as t approaches 0, what we've got in a second bracket, which is a negative 1 over t, approaches infinity, because if as you make the bottom of that fraction bigger and bigger and bigger, it means that as you make the bottom of the fraction smaller and you approach 0, the whole fraction itself gets bigger and bigger and bigger. So as t here approaches 0, the whole fraction is going to approach infinity. You could actually say negative infinity, yeah, because we've got negative 1 over 2. So as a result, the improper integral does not converge, or you could say it diverges, so it cannot be evaluated. Right, let's move on to part B. Let's see if this one can be evaluated or not. So we're integrating between 0 and 2, and it's x over square root 4 minus x squared dx. Now we need to have a think about what the problem limit is going to be. Now if I have a look, can you see I don't want to divide by 0 because 0 is not defined, and there's going to be a problem if I put the number 2 here, which is the upper limit. So let me just write that down before we move on. So I could say in part B, so you wouldn't necessarily write this down in the question, it's just so that you can see what's going on. The upper limit, which is x equals 2, is the problem as we'll basically have 2 over square root of 4 minus 2 squared is not defined, because you'll end up dividing by 0. So just like in the previous one, we're going to replace not the lower limit this time, but we're going to replace the upper limit with t. So the next step, as soon as we press that change that limit, we write this little statement down. The limit as t approaches, in this case 2, approaches this problem value. So 0 and t now are the limits, and I'm going to write my integral as x, and then in brackets 4 minus x squared to the power negative a half. That makes it easier to integrate. Now from the Pure 2 book, you would have learnt that if you see an integral of this pattern, yeah, then we try this, okay, and then you go back and do an adjustment. But to make things a bit quicker, rather than trying f of x to the power n plus 1 and then differentiating it, you could use this in your normal maths as well. If we can make our integral look exactly like this, so that this f of x is exactly this f dash of x, if it is exactly this differentiated, then we don't have to try anything. The integral, once we evaluate it, when we integrate, it'll actually be f of x to the power m plus 1 over m plus 1. So if you can make this exactly this differentiated, then you can go straight to this. This saves a bit of time, and we're going to do that. Now the bit in the brackets here, okay, that differentiated would give me, if I call this f of x, let's just write that down. So this is like our f of x part here, and actually this one is to the power negative a half. then this I want to make it look like f dash of x. So that means actually that it needs to be negative 2x. So now this looks exactly like the brackets there, differentiated. Now I can't just put negative 2x, I've got to keep it all balanced. So I've got to put a negative a half here. Yeah. Now I've done that, what I can do now is just go straight and use this here. So that will be, so still the limit as t approaches 2, and that will be 4 minus x squared to the power a half, so that's n plus 1, divided by a half. Yeah, and I know it's going to be that. I don't need to go back and check it's going to be that. So this, if we can do this, this just saves a bit of time. Right, so the next step is to tidy up what we've got in the brackets here. Oh, and remember that I had this negative a half, mustn't forget about that. So that negative a half I brought outside, it needs to be written here. Let me put it in a different colour just to remind ourselves, and highlight it so that we, just to show you, whoops, highlight it rather than rub it out. So yeah, that negative a half there, that was there, so I must list that out. Right, yeah, so tidying up what's in the brackets, so the limit as t approaches 2. Now I've got a half here, I've got a half here, so half divided by half, that cancels out, that just leaves me with the negative. So I'm just left with negative square root, so that's power half, 4 minus x squared, and my limits are 0 and t. So let me put those in, 0 and t, 0 and t, so that should be square brackets. So let's make them square brackets. Like that. And now we're ready to substitute in and see what happens as t approaches 2. So I will have negative, and it will be 4 minus t squared in the first bracket, minus, in the second bracket will be negative 4 minus 0 squared. Now this is a bit we're interested in here. As t approaches 2, so as t approaches 2, this will get closer and closer to 4, so we'll end up just doing the square root of 0, which isn't a problem. We're not doing the square root of a negative number or anything like that. So we'll just write down as t approaches 2, this negative square root 4 minus t squared approaches 0. So our whole integral will become, so this becomes 0, so 0 minus negative square root 4, so this bit just becomes 4, and basically these negatives become a plus, so square root 4, it just becomes 2. So this integral can be evaluated and it becomes 2. So let's just highlight that. So that will be our final answer for that one. In this example, you may notice a couple of things. The first thing is the limits. We have two infinity limits, so we'll talk about how we do that in a moment. The second thing is the integration here. Now you might look at that and be tempted to do integration by parts. It's going to be a problem, because if we make this bit u, x equal to u, and this bit here equal to dv dx, we're going to run into problems when we try and integrate e to the minus x squared. So whenever you're not sure, we go for substitution. So I'm going to do this integration by substitution. So the thing that you want to substitute is going to be where you've got the function of a function, and it's going to be that inside function. So we'll go for u equal to x squared. That makes the most sense. So I'm going to say let u equal x squared. So then I'll work out du dx, which is just 2x. So at some point I'm going to have to replace dx with something. So if I rearrange that, dx will equal du over 2x. So let's now substitute that integration. So we'll have x. So instead of e to the minus x squared, I'll have e to the negative u. Now notice that I've left the x there because when I replace the dx with du over 2x, what's going to happen? Well, the x will cancel out. So that will leave me with half e to the minus u du. Yeah. So I'll stick the half over the other side to make things a bit easier. So now all I've got to do is to integrate e to the minus u. That's easy. So it's going to be minus e to the minus u. Let's take those just put normal brackets in like that. I probably don't even need brackets, do I? I could just put minus half in front like that. Obviously that's going to be plus c, and then I'll just substitute back and substitute the u back for x squared. So final answer is going to be negative half e to the minus x squared plus c. Mustn't forget our plus c. So that's part A done. Now in part E we've got these two limits which are both infinite. Now what we need to do here is we need to split the integration up so that we go to some real number, let's say from negative infinity to a real number, and then from a real number to infinity. So basically what I'm doing, if this is my number line and I've got, this goes off to infinity at this end, and this goes off to negative infinity in this end, and my two limits, I need to split the integral so that I go from negative infinity to a number, and then from the same number to infinity. Now it makes sense to choose a value like 0 to make it easy. So this is what my integration is going to become. Two integrations from negative infinity to 0 and from 0 to infinity. So any time you've got infinity as both of your limits, then you need to split it, and I suggest we go to 0 to make things easy or easier. So this will be x e to the negative x squared. We're going to split it from into this integration. So from negative infinity to 0 of x e to the negative x squared, and from 0 to infinity of the same integral, x e to the minus x squared. I suppose I should have a dx in there. So let's put dx there. So can you see how this is now split up into two integrations? So I now need to deal with both of these. So let's deal with this one over here. So same technique as before. Let's see what happens. The limit as t approaches negative infinity. So we're going to have from 0 to t. and this will be x e to the negative x squared dx. Now we've integrated this, haven't we, in part A, and this is what it becomes. So we don't need the plus c. So from that we can write down, we're looking for the limit as t approaches negative infinity. Now we could, instead, we could make this limit negative t and see what happens as t approaches infinity. Either way we'll get the same answer. So x e to the minus x squared becomes half, or negative half, e to the minus x squared. So this is basically from part A, and our limits are going to be 0 and t. So what's the limit as t approaches negative infinity? Well, that will be negative a half e to the minus, now this will be 0 squared, minus half e to the minus t squared. Now as t approaches negative infinity, or infinity if you've chosen the limit as negative t, this part here we're going to get a very big power, and as the power gets bigger, this whole thing gets smaller and smaller and smaller. It's going to approach 0. So we can say as t approaches negative infinity, this negative a half e to the minus t squared is going to approach 0. So all of this evaluated is just going to become negative a half. Okay, so I'll put that in a box because we're only half done. So the reason it becomes negative a half, because anything to the power of 0 is 1, so you've got negative a half. This all approaches 0, so we're just taking away 0. So it's going to, the limit as t approaches negative infinity is going to be negative a half. We now need to do the same for this part here. So this time it's going to be the limit as t approaches infinity for the upper limit. So 0 down here and t for the upper limit there, and it's x e to the minus x squared dx. Now we've already integrated this in part A, so the limit as t approaches infinity of this negative a half e to the minus x squared, and limits of 0 and t. So we're almost done. So the limit as t approaches infinity of, so it's going to be negative a half e to the minus t squared minus negative a half e to the negative 0 squared, because that's the other limit. So let's try and squeeze in some brackets there. So let's go up here to finish this off. Now for this bit here, as t approaches infinity, so that's going to get bigger, this whole thing is going to approach 0. So we're only going to be left with this bit here. So we'll just write that down, that as t approaches infinity, this whole bit in the first bracket, which is negative a half e to the minus t squared, is going to approach 0. So that means that this whole thing here evaluated just becomes, well, we've got negative a half, so it just becomes a half. Yeah, so this is for the second bit. Okay, so basically this part evaluated as t approaches negative infinity becomes negative a half, and this bit as t approaches infinity becomes a half. So now we just add the two together, because remember there was a plus sign, we split it up. So our final answer is going to be negative a half plus a half, which is 0. So that's our final answer. That's what this becomes once t approaches these two limits. Right, you should now be able to do exercise 3A on pages 56 to 58. So remember, these improper integrals can be divided into two types. Those where we have infinity as limits. Okay, and the way that you deal with those is that you replace the limit with t. Okay, and then see what happens, what's the limit as t approaches one of these infinities. We could also have improper integrals where the integral is not defined. Okay, in which case then the place where it's not defined, we replace that with t. So replace value where function is not defined with t, and then we want to find out what happens, what's the limit as t approaches this undefined, not undefined value, but the value that gives the makes the function undefined. So as t approaches the value that makes the function not defined, so that's dividing by 0 basically, and where we have limits like this, we've got negative infinity to infinity, what we'll do is we split the integration up so that we integrate from negative infinity to 0 and then from 0 to infinity and beyond.